Good afternoon to colleagues in UK as well as Ethiopia. Good morning in Colombia, and good evening for colleagues in India and Malaysia. So this is actually one of the programs under Water Security and Sustainable Development Hub research funded by UK RI. The program is under Global Research Challenge Fund, headed by Professor Richard Dawson from University Newcastle upon Tyne. This program actually involved 5 collaborators and partners from 5 countries, as I mentioned just now. So, of course, security is very important issues, and climate change is, of course, one of the main focus now, which basically we have to relate impact of climate change to various aspects of water security and management. And this is basically the very first series of the water climate change and water security colloquium series, and we are very fortunate and to have Professor Jim Halls from University of Oxford to be the first speaker. I would say prime speaker, because this is the first series, and we will have similar series every month. Before I start, I would like to brief CV of Professor Jim Hall. In fact, I feel very honored to be given the opportunity to share this session. Okay. Professor Jim Hall is Professor of Climate and Risk in the School of Geography and Environment, University of Oxford. Lead researcher on the Oxford Maritime Program on transboundary resource management. A senior research fellow in the Department of Engineering, Science and Fellow of Linac College. He was the director of the Environmental Change Institute. He is now a member of the Prime Minister's Council of Science and Technology, and expert advisor to the National Infrastructure Commission. Is the chair for the Science Advisory Committee of the International Institute of Applied System Analysis, or IASA, a member of the UK Independent Committee on Climate Change Adaptation. He also has led the development of the National Infrastructure System Model, NISMOD, which is being used by the UK's first National Infrastructure Assessment. Now he is the chair of the UK Data and Analytic Facilities for National Infrastructure, DAFNI. His system analysis is now being used at various places all over the world, various countries. And he is also the editor of Journal of Water Resource Research. So his title this afternoon is Resilient of Water Resource System in a Changing Climate. So before I hand over this screen to Prof. Jim, I think for participants, you can ask questions by clicking the question and answer at the bottom of the screen. You can write the question and later on we can look at the question. With that, the screen is yours, Prof.
Fantastic, thanks. It's wonderful to see so many people on this call. And it's a great pleasure and honor to have an opportunity to talk about some of our research, partly as part of the GCRF Hub, a lot of this coming from work beforehand, to talk about this to you today. The way in which I've framed this talk is, first of all, to present some concepts actually originating from work that a number of colleagues and I did with the Global Water Partnership on the relationship between water security and sustainable development, to give a bit of a conceptual framework. And then I'm going to try and then draw lessons from applied systems modeling, both in Britain and in relation to the Grand Ethiopian Renaissance Dam. There have been a lot of collaborators in all of this. For the first part, as I say, I should acknowledge the Global Water Partnership and the OECD, and my co-chairs of that initiative, Claudia Sadoff and David Gray. The second part has been a cast of 1,000. Some of you on the call may even recognize some of your work. It's primarily been funded by a UKRI NERC project called Marius on drought risks in Britain. And then the third part of the work has actually almost entirely been done by my colleague Kevin Wheeler, who I collaborate with closely, but Kevin is much more of an authority on the Nile and the GERD than I could ever possibly be. But I think it's nice to put these two pieces together because it illustrates actually how there's a convergence of methodologies here. I don't kind of buy the water and development exceptionalism arguments. I think actually in the context of a changing climate, in the context of rapid industrialization in most developing countries around the world, we're actually facing a very similar set of water-related issues and risks. And in that sense, we can learn a great deal from one another. And these two examples, the work in Britain and the work on the Blue Nile, have certainly learned from one another, and you will see some strong methodological similarities. But to begin by providing some conceptual framing, in a sense, we need to begin by answering the question, why are we worried about water? And the framing we developed within the GWP project, Securing Water Sustaining Growth, was that at the center of this is measures of prosperity, health, well-being, a broad sense of what it is to lead a good life, if you like. Water influences that, and the starting point is the water endowment. What is the nature of the hydrology which any particular country happens to have by virtue of its geography? And that water endowment contains hazards, contains extremes, floods, droughts, water quality related hazards, and those water related hazards combine with exposure and vulnerability to create water related risks. And those risks impact on what we value, on prosperity, well-being. So that's the first reason we worry about water, is because water-related risks are a threat to what we value. And in fact, particularly in advanced economies, which have in many senses overexploited their water resources by now, water-related risks are the main reason why we worry about water. We're worried about droughts, floods, harmful water quality. There are, of course, productive opportunities associated with water. So in particular for developing countries, maybe looking also at those opportunities which come from the aquatic environment. As I say, in advanced economies, a lot of those opportunities no longer exist because water has been overexploited already. And we set out this concept in this paper in Science some years ago, which made the point that the risks from water impact upon development, but we can respond to those risks with a series of water security interventions, which is around water-related institutions. So the ways in which we manage water, and those institutions need information. And it also entails things on the ground, infrastructure, which are part of the water resource system. And so those investments in water security, in information, institutions, infrastructure, help us to access those productive benefits from water and help us to manage the risks. So investments in risk reduction, in protective infrastructure. And so by investing in this way, one can more sustainably access the opportunities and manage the risks to growth, wealth, and well-being. The final thing to note in this is that there's another feedback, which is that economic development itself increases exposure to water-related risks. And so we need to keep an eye on that upward driver on risks when we're planning for investments in water security. Because if countries are developing, their exposure to water-related risks is bound to increase. Within this same piece of work with the Global Water Partnership, we very kind of tentatively sketched out some trajectories of those risks. We observed that the impacts from inadequate water supply and sanitation, in many senses, the greatest water-related risk in the past, thanks in part to the MDG and now SDG 6 and the work of the Joint Monitoring Programme and so on, is those risks are coming down. I'm not underestimating them, but there is something of a partial success story. Meanwhile, lots of both empirical data sets around the impacts from flood related hazards, river and coastal flooding, and model results are telling us that river and coastal flood risks are on their way up and show no sign of abating. The risks of droughts and water scarcity are also on their way up. In many parts of the world, the climate is becoming more arid, but there's in some senses more in the way of adaptation going on in relation to those risks. So again, very tentatively, we put those risks somewhat lower in the future. And in many senses, the risks of ecosystem degradation and pollution have been going up the fastest, but also including in many rapidly industrializing countries where this is happening fastest, we're seeing increasing attention to these risks and the potential to manage those risks down through, in particular, through proper regulation and infrastructure for wastewater treatment. Very tentative, and I'm sure there will be questions in the chat which might challenge that interpretation of the trajectories of water-related risks going into the future. In subsequent work, and this was done by one of my PhD students, Tess Doffinger, with Claudia Sadoff and Bill Young at the World Bank. We took that kind of conceptualization and turned it into this water security dashboard applied here for Pakistan, where we look at what are the drivers which are driving risk into the future. So those population, urbanization, economic development drivers, and what are the environmental drivers as well, in terms of what's happening with the climate. And then what is the water endowment? So how much water is actually there in a country? How might that be supplemented with unconventional water sources? And then what is the usage of that water? And how is that usage being mediated by infrastructure? What are the institutions there to manage water? So those all, you might think of those as being system state descriptors. And then we get on to the outputs and outcomes from the system. So what's the frequency of water-related impacts, water stress, water pollution, and then what are the outcomes for people and the environment? How are we doing with respect to access to improved sanitation, deaths from flooding, economic impacts from floods and droughts? How is the aquatic environment doing? And I'm sure also you can think of ways of supplementing or improving upon a dashboard like this, but I hope you can see the kind of conceptual link between the framework I started with and how you can begin to attach some numbers and trends. You can see what the arrows here depict what's happened in the past and what is our projections of what will happen in the future, to provide a means of managing water security at a national scale. Now, let's dive a little bit deeper into the way in which that water resource system works and how we might model it in order to inform decision making. And this is a very simple depiction. This will all be familiar, but just to make sure that you've kind of got the same sort of mental picture of this thing I'm referring to as a system as I have, which is a watershed, a catchment with some rainfall and runoff, and then withdrawals or diversions from that system, storage in reservoirs, waste water treatment plants for urban areas, diversions for agriculture, discharges into wastewater treatment plants, possibly reuse or discharges back into the aquatic environment. So this is the water resource system we're all thinking about. And there are many ways of modeling these systems. That's all quite well established. One way of doing it uses this type of sequence. So we're interested in looking very carefully at hydrological variability and how that might change going into the future. So that requires time series analysis to capture that variability. And that's why we often start this type of analysis either with weather generators or with stream flow generators. This weather generator is the one developed in Newcastle, which was also adapted to represent transient future climate scenarios. That provides simulations of rainfall PE, which can go into a hydrological model to simulate runoff, or one might start with a synthetic stream flow generator. And then that provides the inputs to a water resource system model. So this is modeling the system I just showed to you conceptually. So the flows of water downstream through the catchment, the water withdrawals, the points of water use, and then the discharges back into the system, the water storages as well. And alongside the surface water resources, we need to put groundwater withdrawals in there too. At some points in the system, there are some critical operations, control of the reservoir. This picture here just depicts the system in the Thames Basin, and that is primarily controlled based on flows right down at the bottom end of the catchment, down at Kingston. And this diagram is the Lower Thames Operating Agreement, which determines how much water can be withdrawn from the system at different times of year, depending on the flow in the river. It's important that these types of models are credible, that they represent the system in a way that corresponds to what's been observed. And one of the observables in this type of system is the reservoir levels. So we pay quite a lot of attention to making sure that the calibrated model can reproduce reasonably convincingly the reservoir levels within the system. And where this gets you, by running lots of those synthetic series through the model, we can get to our water security outcome of interest, which in this context is water shortages. How often, what percentage of the time or what probability annually is of users of water in the Thames Basin not having water. Now that is it is a pretty rare event, but there's still some finite probability that that might happen, and the impacts of that would be enormous. One estimate suggests around 400 million pounds per day would be the lost economic activity. And so by doing these simulations, we can plot how that probability of water shortage might change in the future. And this is the black line, which just shows the impacts of climate change. Increasing aridity primarily is what's driving that. But then we're looking at some scenarios of what might happen on the demand side. So if population increases, which it is projected to do in the southeast of England, then this risk of water shortage goes up very significantly. And then the green line shows what happens if those abstraction rules, the limits on how much water can be taken out of the river, become more stringent because the river is being over abstracted. And this is very much the debate at the moment, how much water should be restored to the aquatic environment to improve the environment. But if you're able to take much less water out of the river, then that pushes up the impacts of water shortages. So this type of analysis helps us to understand those trade-offs. And then the other thing we can do is, well, let's look at how effective might be some of the options which we have in mind for managing this risk. So here we're looking at a big reuse plant. The black is the baseline. The blue looks at what might be achieved through demand management and leakage reductions. And then if a big new plant is introduced, that's a big amount of additional supply to London, and that could effectively bring the risk down by a lot. And the way in which we kind of increasingly think about these things is in terms of dynamic adaptive pathways. So thinking about portfolios of different adaptation interventions which are introduced into the system through time. So here's another dashboard. The top one shows the supply side, so different simulations of flow, which vary a lot and are gradually ticking downwards because of the increasing aridity. The second graph shows the demand side, so how the population is increasing and what that might change by in future. And the third one shows how much water might we save, or new water might we be able to provide with different adaptation options: efficiency improvement, demand management, price reform, that wastewater reuse plant that we referred to previously. And so then the bottom panel shows how that all adds up to create a projection of risk running through time. We see the risk ticking up, going through towards 2050 because of the increasing demand, and the adaptation options are not enough to keep up with that increased demand. Then as the new plant comes in, the risk goes down. But after that, unless we do more about these additional demand drivers, then the risk will continue to go up, though the uncertainty, which is the width of the band, that increases into the future. That was all for the Thames Basin. The most recent work that we're doing has begun to look at all of England and Wales. We were part of a big study for Water UK in 2016, which began to look at, on a very large scale, at strategic water transfers in order to address these water scarcity issues in the southeast of England. That's why it's all red down there. So the question is, how can these strategic options begin to redistribute the water in order to address these very big issues? The northeast, where some of this audience is comfortably green up there. And so national picture is a more difficult calculation because you have to pay a lot of attention to the spatial structure of the droughts. And so for that, we developed a new spatial drought event set. This is based on downscale climate model outputs. We're using bias corrected regional climate model outputs, very large ensemble of that for this. And this is just the 10 most severe droughts in that large ensemble, which then goes into national rainfall runoff modeling using a model called Decipher, developed in the University of Bristol by Gemma Cox and Jim Freer and colleagues. And then this increasingly elaborate national water resource system model, which a whole series of postdocs working in my group, Mohammed Mortaza Naini, Barney Dobson, and now Gökhan Kurulugu are working on. And this model is being used now by Ofwat and the Environment Agency to test out those strategic options and work out how effective might they be at reducing risk. This picture here, the vertical axis is that probability of water shortages, so big is bad. The horizontal axis is the simulated duration of the restrictions. And this is really important from a resilience perspective. What we're worried about is not only how often the bad stuff happens, but also how long does it last? How quickly can we recover? That's inherent in our understanding of resilience. And so these plots show for different regions of England and Wales, what's the risk now, what that might be in the near future and the far future. And the work we're doing now is looking at how effective might those strategic options be at reducing this risk. So then seamlessly, I transfer to the Eastern Nile and pick up on the work that several colleagues and I have been doing, led by Kevin Wheeler, simulating the Eastern Nile in very much a similar way as I just described that framework for the Thames. We start with a synthetic stream flow generator. So we're not directly using climate model simulations and rainfall runoff modeling. Those of you who know the region well will recognize the issues with climate models in East Africa and not being able to explain the variations in, for example, lake levels that have been seen in recent decades. But Kevin has developed a very complete model. I think we would say the most complete model of the Eastern Nile in terms of description of the system, the operation of the GERD, and of the high Aswan Dam, and all of the intermediate dams and demand centers. And we've been using that to analyze the implications of the GERD, both during filling. And the good news here is that the lake levels in Lake Nasser at the high Aswan Dam are quite high at the moment. And so the impacts of the GERD are during filling are unlikely to take the high Aswan Dam levels down to a level which would lead to shortages. There's a very low probability that will happen, though it does depend, of course, on the filling strategy, which is adopted at the GERD, which is the centerpiece of the negotiations at the moment. We then go on to look, and you'll see here also that these graphs are based on historic traces of Nile flow hydrology. I mentioned that we use synthetic hydrology, but often for discussions with decision makers, it's very reassuring for them to see traces from the historical flow record to look at the what if the GERD had been built and this series of flows took place. And so here we're looking at storage levels at the GERD in blue over a 20-year period at the beginning of the 20th century, 1930s through to 1950s. The black dotted shows what happened to the lake levels at the high Aswan Dam before the GERD was built. Obviously, it wasn't built at that time. And then the black solid line shows the counterfactual of the levels with the GERD in place being operated. It depends a bit on whether you operate the GERD to maximize power reliability or to maximize total energy production. But nonetheless, the story here is that under fairly average hydrological conditions, the GERD will mean that at the highest Aswan Dam, the water levels will be a bit lower, and that's going to be observable. And there will be less fluctuation in water levels, but nothing under normal conditions which should cause much in anything really in terms of the risks to water supplies in Egypt. Of course, what's critical is how this system is operated during a drought. And so to analyze that, we've looked at the 1972 to 1997 record, which was a severe drought. And at the bottom, you can see a plot of shortages. So in a drought like this, there would be shortages in Egypt. There would be what the GERD does is delays those shortages because it provides some additional storage upstream, but then the shortages kick in. And the critical question is how the GERD is operated at the end of the drought when both reservoirs, both the GERD reservoir and Lake Nasser, are pretty much empty. Is the water immediately stored up in Ethiopia to fill the GERD back up as quickly as possible, or is some of it transferred downstream to alleviate the risks and impacts which are being felt in Sudan and Egypt at that time? And that is the critical agreement that needs to be reached now. Is can a risk sharing arrangement be arrived at, which would enable drought risk management when that next severe drought hits? And we know it's inevitable that there will be another severe drought at some point in the future. And the point that Kevin and other colleagues, Dale Whittington, amongst them, have been making is that an agreement needs to be reached now on how that drought is managed when it hits. So that's taken you through three things: some framing in terms of how we think of water security as a process of risk management, and climate change manifests itself as increasing water-related risks to people in the environment. And in fact, I think we can argue that water-related risks are amongst the most, if not the most, concerning impact from climate change. To manage that risk, what I've been talking about is the use of water resource system models for planning purposes, which enables us to construct synthetic versions of the systems that reproduce the climate, the hydrology, the infrastructure, and the way in which that infrastructure is operated in order to allocate water to people and the environment. And we can validate those with respect to the existing system and then use them to test a wide range of possible future scenarios, both climate scenarios and scenarios of socioeconomic development. Then look at a wide range of adaptation options of the possible ways in which we can intervene in this system to manage risk, and test those options to see how effective they are at reducing risk. The benefit of an adaptation is how much it gets risk down by, but it will never eliminate risk. There's always a residual risk. But we can look at not only one adaptation option, but as what I referred to here as portfolios. I referred to that in the Thames Basin, also at the scale of all of England and Wales. There's a very large number of combinations of interventions. We want to look at the combinations and sequences of those interventions. And that enables us to understand how risks to different actors, be they urban populations or farmers or power producers, including how the poorest fit amongst those different actors, how do those risks evolve in the future, so that we can identify and implement adaptation pathways that equitably manage those water-related risks. I hope that makes some sense. We've obviously written a lot of papers about this. In fact, we've written a lot more than this. This was just as many as I could put on the page. But the main purpose for putting this up is that by scanning through the authors, you will see all of the people who have also contributed to this work. And I'm most grateful to all of those and very much acknowledge them.
On behalf of GCRF, Water Security and Sustainable Development Hub, we would like to thank you so much for your lecture, for sharing your knowledge and experience in dealing with the climate change risk. Thank you so much.
Thank you, my pleasure.